In this video, I'm going to talk about the solution to the questions in the midterm 1 review. Okay, I'm going to talk about the solutions one by one. So let's start with the first question. The first question is to compute the Laplace transform of a function, typically in the time domain, which is given by t plus e to the minus 2 times t minus 1. Okay. So here I'm going to show you how to compute the Laplace transform. So we can basically use the linear property for the Laplace transform. So the Laplace transform of t plus e to the minus 2 times t minus 1, I can sort of split them. So as the sum of two, one is the Laplace transform of t, and the Laplace transform of e minus 2 times t minus 1. Okay, so this one we can use here basically I can use a table. So this one use a table to find out what is the Laplace transform, which is 1 over s squared. And this guy, we don't know, we don't have, the table doesn't show this explicitly, but we can change this one a little bit so basically write this e to the minus 2 t minus 1 as e minus 2t and plus 2. Then we separate them as this is L of e minus 2t times e to the 2. E to the 2 is a constant, so we can move it outside. So we'll keep the first one to be the same, and then we move the e squared outside, which is L to the e minus 2t. This one we use the table again. So we can have, this is the e squared times 1 over s plus 2. Okay. Of course, you can also use the definition directly to compute the integration in this way. This will be more complicated, but using the table will be much simpler. Okay, let's go to question 2. Question 2 is to compute the inverse Laplace transform of a function in the S domain. Typically, is given by a numerator divided by some denominator, given by this form. Okay. So in the class, I talk about 3 different cases to compute the inverse Laplace transform. It depends on the poles of this function. Okay, because the poles are actually given by s plus 2 times s plus 3, which is set to be 0, and the final solution. The solution is s is negative 2, s is negative 3. So these are real and distinct poles. So it fall under the case 1. So which means this one can be written as a divided by s plus 2 plus b divided by s plus 3. So you just separate these two terms, and then you put the constant a and b. So we have to figure out what is a and what is b. Okay, so a and b, it turns out pretty simple. So if you follow the notes for the how to compute a and b, so a is just given by the original whatever the function in S domain time s plus 2. So this will be the same. Essentially, this will be the same. So you time this one, and then you set this value to be exactly s plus 2 equal to 0. So which means s equal to negative 2. Okay. So when you do this one, so this will be cancelled out. Okay. Then it becomes, so this will cancel out, become 2s plus 5 divided by s plus 3. 1s is equal to negative 2. So by doing the calculation, we get that a is 1. Similarly, b is given by when we multiply the original the function we have over here times s plus 3, and then we set s is equal to negative 3. So here again, this will be cancelled out. Sorry, here this one. So then we just, by replacing the values, we have 2s plus 5, replace s by negative 3, so get this 2 times negative 3 plus 5, divide by here is negative 3 plus 2. Okay, so this give us 1 again. So a is 1, b is 1. So we can have 2s plus 5 divided by s plus 2 plus s times s plus 3. Here is given by 1 over s plus 2 plus 1 over s plus 3. So once we have that, the inverse Laplace transform of this guy is just equal to inverse of this individual component by using the linear property of the inverse Laplace transform. So then we can separate them as L inverse as 1 over s plus 2 plus 1 L inverse of 1 over s plus 3. So again, here we use a table. We can figure out the actual inverse Laplace transform for each of this component, which is given by e to the negative 2t plus e to the negative 3t. Okay, for question number 3 is try to compute the solution of a differential equation by using the Laplace transform and the inverse Laplace transform. Okay, so the differential equation is given by 2 times x double dot plus 3 times x dot plus x. So here, of course, I mean by this is given by t plus, this is given by t, this plus xt. So it should have time. And also I have initial values are x0 being 0 and x dot 0 being 0. So to make it a little bit simple. So the first question is to compute the solution of the differential equation in the S domain. Okay. So to make it, so notation wise, we use the capital XS as a Laplace transform of LXT. Okay. By doing that, so we're going to do what we want to find. If we want to find a solution in the S domain, we want to apply Laplace transform on both sides. So once apply the Laplace transform on both sides, for the left hand side we have L Laplace transform of 2x double dot. So this one has to be t, this is t, this is t again. And right hand side is Laplace transform of 1. Okay, so we can separate those. Let's do this one. This is a t, this is t, this is a t. Okay, so by using linear property, so this becomes, I can also move the constant value outside, so it becomes 2 times L x double dot t plus 3L x dot t plus L x t is equal to L of 1. Okay, L of 1, this is just 1 over s. Okay, so you use a table. So this is, you use a table. Find a 1 over s. Okay, and this one you can also check the property of the double derivative and the derivative. Okay, so for x double dot t, the Laplace transform is just s squared times xs minus s times x0. This is x0 defined here, and minus x dot 0. This is initial values of xt, and this is initial value of x dot t. Okay, and for the x dot t, the Laplace transform is 3. Keep the 3 over here. Is s times xs minus x0. So this is also initial value. And then the L of xt is defined over here, it's just xs. Okay, so by using the property x0 is 0, x dot 0 is 0, so this will be gone. Okay, this 0 is gone, this 0 is gone, this 0 is gone. Okay, so we simplify quite a bit. So I have 2s squared times xs plus 3s xs plus xs. That's what I have, and the right hand side is 1 over s again. So by doing that, I have 2s squared plus 3s plus 1 times xs is 1 over s. So xs is 1 over s times 2s squared plus 3s plus 1. So that's the solution in the S domain. Okay. The step 2 is find the zeroth pose of xs. Okay. So 0 is when you set the numerator to be 0. Apparently there's none. You set it to 0. There's no solution to that. So the zeros are none. So when I say it's the numerator, you set it 1 to be equal to 0. There's no solution to this. This is none. Suppose you set the denominator to be 0, which is s times 2s squared plus 3s plus 1 equal to 0. So this one we can do a little bit simplification, which is s times 2s plus 1 times s plus 2 equal to 0. So now I have 3 poles. One is s equal to 0. The second one is s equal to negative 1/2. And last one is s is, this one should be negative 2. Okay. Negative 2. Okay. So that's one. I think this has to be 1. Okay, this has to be 1. So this is negative 1. Okay, so s is negative 1. So that's my pose for the xs. Okay, so the final question is for the final step for the question number 3 is, does the final value of xt, in other words, the limit of t go to infinity xt exist? If yes, what is this value? So actually this question asks about once we find a solution in the S domain, what is the solution in the time domain? Okay, all right. So So this one we can use, of course, first of all, we can compute what is xt, since this one we already have the form over here, so which is 1 divided by s times 2s squared plus s plus 1. So the first approach we can do is to find the value is, well, I can just find out what is xt, okay, by using the xs. I use the inverse Laplace transform to find xt. So you can use the 3 different cases based on the pose. Apparently this is the real and distinct pose. You still use case 1, okay, so this is still case 1 for the if you check my video for the inverse Laplace transform, it's just case 1, which means I have here, so my xs is a over s plus b over s plus 1/2 plus c over s plus 1. So that's what we have. So just figure the a and b and c, then you can find the solution. You can do the inverse xs. Okay, I don't want to repeat it over there. So you find xt, then you find the final value to see if it exists. The limit exists. Okay. The other pretty similar approach is we can use a final value theorem. Okay. By using a final value theorem, we need to verify if the poles of xs are in the open left half plane except 1 as the origin. Okay, to check this is true. If you look at the poles, okay, the poles are 0, okay, at the origin. This is the open left half plane. Open left half plane means the real part of your poles has to be in the less than 0. So this is the real part is negative 1/2, is negative 1, so it's negative. This is the open left half plane. So yes, we can use the final value theorem. And if we can use the final value theorem, we can also say the final value does exist. Otherwise, you cannot find the final value. If this is true, we can always say the final value exists. Okay, and in particular, the final value of xt when t goes to infinity is given by the limit of s goes to 0 of s times xs. Okay, so by substituting the xs by what we already computed over here, right over here, so the limit s goes to 0, s, don't forget about this s times this xs, I just copy the xs over here, is 1 over s times 2s squared plus s plus 1. So this s will be cancelled out. It's just the limit of s go to 0 is 1 over 2s squared plus s plus 0. So we just replace s by 0. Okay, so it's 1 over this whole thing, so this will be gone, so this is 1. So it's 1 over 1, so it's 1. So the final value is just 1. Okay, this is question number 3. So let's go to the question number 4. Okay, question number 4 is also about the differential equation. So we still talk about differential equation. The problem is we want to compute the solution in the s domain, and then use the partial fraction expansion to find its solution in the time domain. Okay, so the differential equation give is, let's still put the time domain t over here. So it's x double dot t minus xt minus x dot t minus 2xt, which is 0. Okay, and the initial value x0 is 0, x dot 0 is 1. Okay, this is different. Okay, so we'll first have to compute the solution in the s domain, then use the partial fraction expansion to find the solution in the time domain. So I'm going to correct a little bit over here. So this one is, yes, okay, I think that's correct. Okay, so first let's compute the solution in the s domain. So again, we can use the Laplace transform for both sides. Okay, minus 2xt. Okay, so we apply the Laplace transform for both sides of the equation, and then we use the linear property. Okay, use the linear property. Okay, and then we by using the notation xs is lxt. Okay, now we have this form. We have this one. So again, we use the same property I mentioned over here. The property I mentioned over here. Okay, so we do still have, this is s squared xs minus sx0 minus x dot 0, and minus, this is the lx dot t, is s times xs minus x0, and this is minus 2x0. So here we have the initial value of x dot 0 is non-zero, x dot 0 is 1, so this is 1. Okay, this is 0 is gone. Okay, this is gone. Okay, and this is also gone. Okay, so I have s minus 1 minus s times xs minus 2xs equal to 0. Okay, so once we put them to the one to the right hand side, okay, then we put them together for the xs, so we have s squared minus s minus 2 times xs equal to 1. So xs is just given by 1 over s squared minus s minus 2. Okay, alright. So the second step is we want to use the partial fraction expansion to find the solution in the time domain. Okay, so how do we do that? So it's the same as we talk about the xt, as I mentioned in the previous example. You do the inverse of xs, and which is the inverse of 1 over s squared minus s minus 2. So this I just replace this xs by this. Okay, put it over here. To figure out what is the inverse Laplace transform of xs, so we can use a partial fraction expansion. So there are 3 different cases I mentioned before. So those are based on the poles of my xs. So to check the poles, I set the denominator of the xs to be 0, which is I set s squared minus s minus 2 to be 0. So I end up having 2 poles. One is 2, one is negative 1. So they are real values. They're distinct, they're different. So real distinct is still fall under the case 1. So which means my xs can be written as a divided by s minus 2 plus b divided by s plus 1. Okay, so we just have to figure out what's the value of a and what's the value of b. Okay, alright, again, so we can use the same approach as I mentioned in the second question. So a is given by the original xs times s minus 1, then evaluate at s being 2, okay, s minus 2, sorry, and which is equal to 1 over, we just replace s by 2, so it's 1 over 2 plus 1 is 1 over 3, okay. So b is the same way, so I don't repeat over here. You do the same approach, you figure out as a b, which is given by a negative 1 over 3. In other words, we have 1 over s squared minus s minus 2 is 1/3 divided by s minus 2 plus negative 1/3 divided by s plus 1. Okay. So once we have that, the xt is the inverse, L inverse of this the original one, which is just inverse of the individual by using linear property. Is the L inverse of 1/3 s minus 2 plus 1 negative 1/3 s plus 1. So by using linear property, it's the individual, we take the inverse Laplace transform of the individual component over here. And then we use a table again, which is 1/3. So you can pull this 1/3 outside. So this you can consider as a scalar one. You can put a 1 over here. So 1/3 e minus e2t minus 1/3 e negative t. Okay, so that's my final solution for the xt. Okay. All right. So this is question number 4. Okay. So now let's go to question number 5. The question number 5 is about a block diagram. How do we compute a transfer function for the block diagram? Okay, so the block diagram is pretty simple over here. So we just have a negative feedback loop. Okay, so for the negative feedback loop, the transfer function is, the first question is to compute transfer function of this block diagram. The transfer function is actually given by ys divided by rs, which is for the feedback loop. A negative feedback loop is whatever we have over here is 2s plus 3 divided by s squared plus s minus 1 divided by 1 plus the product of this loop. So it's 1 plus, if it is negative feedback, this is plus, okay, because this is negative, so this is a plus, okay. If this is a plus, this will be negative, okay. So they're just directly opposite. So this is what going through this loop from the is to ys. So this is what you put as a numerator. Denominator is 1 plus the product in the loop. So 1 plus the loop is this guy, feedback loop is this guy, time 1. Okay, so 1 times this whole thing. Okay. Once to figure out, simplify this whole a little bit, so we just time the denominator and the numerator denominator by s squared plus s plus minus 1. So the goal is to cancel out this denominator here. Okay, once we do that, so we have this will be cancelled out. Okay, will become s2s plus 3, and this guy, this one is time 1, so we just copy it over here, and this guy will be cancelled out over here, so it's plus 2s plus 3. So by simplification, I have 2s plus 3 divided by s squared plus 3s plus 2. So that's my transfer function. The second question is, given Rs being 1, okay, to compute, our goal is to compute yt, okay. So first one, before I compute yt, we first compute what is ys. So ys is the transfer function time r sub s, okay. So input is rs, the transfer function is ys over rs. Once we do that, the transfer function, as we already computed over here, is 2s plus 3 divided by s squared plus 3s plus 2 time rs. Rs here is given by 1. So it's time 1, which is just itself, the transfer function itself. The next step is we try to figure out what is yt. So we need to compute the inverse Laplace transform using partial fraction expansion. So again, to compute the inverse Laplace transform, we have to figure out which case does this fall under. Okay, we need to compute the poles. The poles are actually given by setting the denominator being 0, which we set this to be 0, so we get poles are s equal to -1 and s equal to -2. So these are real and distinct poles. And once we have that, we can sort of write this L inverse of this guy can be written as, okay, this is a case 1, okay, of the partial fraction expansion for the inverse Laplace transform. So it's given by a divided by s plus 1 plus b divided by s plus 2, okay. So those are the steps how we figure out the a and b, okay. This is exactly the same approach, same steps we used for question number 2, okay. A is just given by the y of s times s plus 1, then evaluate at s equal to -1. So by computation, we get a is 1. Similarly, we get a b, or the computation follow the same procedure. We get a b is also positive 1. Okay, once we have that, we have L inverse of this guy. We replace a by 1, b by 1. So the L inverse of 1 over s plus 1 plus 1 over s plus 2. By using linear property, is just the inverse Laplace transform of 1 over s plus 1 plus L inverse of 1 over s plus 1. So this one by using table, okay, again, this also using table, this is E minus t for the first one, and for the second one, E minus 2t. Okay, so that's the solution for yt. The question is to compute the final value of yt when t goes to infinity. Since I already computed this value is over here, what we do is just set a computer limit. Okay, apparently the limit, this guy will be 0, this guy will be 0 too, so the limit of these two will be just 0. Okay, question number 6 is how to simplify a complicated block diagram to find the transfer function. Okay, so this is the diagram where you are given, and the goal is to compute the transfer function y sub s divided by r sub s. Okay, right. So this is the key concept of this one is to move this because this one you cannot consider this as a cascade unless we can move this backwards. This one also we cannot consider it as cascade unless we push power forward or backward. Okay, so naturally it's easy to move from using backward order. We move from right hand side, okay, from the y-s then back to r sub s. Okay, so let's see what we can do. If we can move this guy to the right hand side, if this one to the right of this s, then I can have a cascade. Okay, in order to move this on the right hand side, so I sort of have to, this is what I do, this one I move to the right hand side, okay, but I cannot just have a 1 because this one you time s. So to make sure I have the same signal, I have to have 1 over s. You can check the property when you shift it forward or backward, okay, for the block diagram. Okay, so now if you shift this to s, so you get a 1 over s. Okay, if you want to pull to the right hand side. Okay, once I put out right hand side, so this one you can put them to, because once I put the right hand side, now this become cascade over here. So cascade is just the product of these two, right? I can take the product. It's just 1 over s plus 1 times s. It's just s divided by s plus 1. Okay, so this is a cascade. And then I have feedback loop. Okay, the feedback loop, if you talk about feedback loop, this is just given by s divided by s plus 1 divided by 1 plus s divided by s plus 1. Okay, let's put over here, this is negative sign over here. The reason this is true because you have negative feedback. This is called negative feedback. This is a negative feedback. If you check the problem, negative feedback, it's just what's going through here is s divided by s plus 1 divided by the loop. When we have this one over here, we don't have anything over here, which means this is 1. Also, this means 1. Okay, so it's 1 is divided by 1 plus 1 times this loop. In the loop is 1 times the s divided by s plus 1 is 1 plus s plus 1. So if we simplify, if we multiply both the numerator and denominator by s plus 1, okay, so we have s divided by s plus 2s plus 1. Okay, that's the whole thing, which means I have this. I have here should be s 2s plus 1. Okay, so this whole thing become 2s s 2s plus 1, and this have a loop over here. Okay, now this one here again, this is 1, right? This one, you have to move this one to the backward. Okay, because when I have over here, once I have this one over here, simplify over here, I still cannot do this one cascade over here because I have to move this one backwards. What I do is move this one backwards. You don't move it backwards because this is s 2s plus 1, so this one has to be directly the proportion to this one. So I have to do 2s plus 1 divided by s. So then that's where equivalent as if I move this one over here, this is the same as 1. Okay, we have to do the product of these two. Okay, once you do move backwards, I have 2s plus 1. So when you remember this, whatever you move backwards, whatever you have over here, this is 1, this is 1, this is 1. It's just divide by this value. So the same approach, if you move this 1 backward, you divide by this 1. That's why it's just 2s plus 1 divided by s. Okay? Now, once we have that one, we have s. So here should be, okay. Now this one I should have 1 over s. Okay. Once I have 1 over negative 1 over s, and then this is just s divided by s. What I compute over here, this whole block will be just s divided by s plus 1, 2s plus 1. Alright, so then I move it to the right hand side. So this guy, when I take a product, this 2 cascade will be just 1 over 2s plus 1. That's cascade. And also have feedback loop. Okay, so this whole thing, this blue one. Okay, this blue one right over here. This blue one, this is just 1 over 2s plus 1. Okay, this is cascade. And then I have the orange one. This is a negative feedback loop. Okay, this negative feedback loop is this computed by 1 over 2s plus 1 divided by 1 plus. This is still negative feedback. Remember here we have 1 over s is 1 plus 1 over s times the whole thing 1 over divided by 2s plus 1. So if I time this numerator by s 2s plus 1, also here time s 2s plus 1 over here. So this can be simplified as s divided by 2s squared plus s plus 1. Okay, so if we do over here, this whole orange stuff becomes this. So I replace the whole orange stuff by s divided by 2s squared plus s plus 1. So I keep still 1 over s over here. I still keep the feedback over here. This one is a negative 1, still a negative 1. Okay, now I still have a last cascade over here. This is again is a cascade. Okay, the cascade is just given by when you do the product, which is given by this s will cancel out. So it's the product is 2, right? So it's 1 over 2s squared plus 2 plus 1. I still have feedback at 2s plus 1 divided by s. So finally, using the negative feedback is what's going through over here is 1 over 2s squared plus s plus 1 divided by 1 plus 2s squared 2s plus 1 divided by s times the whole thing. Is just whatever you have in the loop, you do the product of everything. Okay, so it's 2s plus 1 divided by s times 1 over 2s squared plus 1. Okay, when you simplify a little bit, so it becomes s divided by 2s cubed plus s squared plus 3s plus 1. So that's my transfer function. Okay, so basically if I go over the steps, so I pull to the right hand side, okay, so I can use cascade and use feedback loop to simplify. So once I do that, because I still have, I go back over here, okay, once I do that, I sort of have this, when I have cascade over here, now I have to move this one backwards, okay, because otherwise I cannot do cascade. So I move this one again, doing move backwards, I have cascade and feedback loop again, and then I try to do cascade and feedback loop again. So that's what happened to simplify the complicated block diagram to find the transfer function. Okay, this is question number 6. Okay, question number 7. This is the last question. So the last question is also given a block diagram. It's a little bit complicated than question number 5, but much less complicated than question number 6. And see, suppose we have a negative feedback loop given by this, which we have a couple component GCS. GCS is given by 1 over s plus 1, and HS is given by 1, and GS is given by 2 divided by s plus 4. And it's a negative feedback. The first question is try to compute the transfer function of ys divided by r sub s. Okay, so this is basically we have cascade and also feedback loop. It's fairly simple. So the cascade, here I replace the value we have defined for GCS and GS. Basically we have this is 1 over s plus 1, so this is GCS, and this is GS is 2 divided by s plus 4. Okay, and we have unit negative feedback. Okay, all right. So this one we have cascade. Cascade is given by this cascade. Okay, cascade. That is 2 divided by s plus 1 times s plus 4. And then we have feedback loop. We have feedback loop, right? Negative feedback loop is which is given by 2 divided by s plus 1 times s plus 4. Because the negative feedback is divided by 1 plus. Okay. Then whatever in the loop says is here, whatever cascade or computed, and this is 1. So this guy times 1, because this is, you can see this is 1. So it's 2 divided by s plus 1 and times s plus 4 times 1. So if we simplify, we multiply both the numerator and denominator by s plus 1, s plus 4, and here again a time s plus 1, s plus 4. So I can get 2 divided by s plus 1 times s plus 4 plus 2, which is 2 divided by s squared plus 5s plus 6. Okay. The second question is compute the limit of yt when rs is 1 over s. Okay. So when rs is go over 1 over s, I have a ys which is rs and time ys over r sub s. Okay, so this is the output is the transfer function times the input. Okay, so the r sub s is just given by 1 over s. Okay, the transfer function what the computer over here given by this is 2 divided by s squared plus 5 plus 6, which is given by 2 divided by s times s squared plus 5 plus 6. Okay, because I want to compute the limit of y sub t. Okay, so the first one we can compute it to see if we can use the final value theorem, right? Because that's the easy way. We don't have to compute yt. Okay, or we can compute yt and find the final value, or we can see if we can use the final value theorem. Okay, to use the final value theorem, I have to check the poles. So poles are computed by setting the denominator to be 0. So we have set it to be 0, which is s. This can be written as s plus 2 and s plus 3. You set it to be 0, so we have 3 poles. One is 0, one is negative 2, one is negative 3. So according to the final value theorem, if we use the final value theorem, we must have only one, at most one as the origin. Yes, we just have one at origin. And all other poles are in the open left half plane. In other words, the poles must have negative real parts, which is true here because the real parts for this and this, they are all negative. Okay, so we can use the final value theorem. The final value theorem says limit of t go to infinity of yt is the final value theorem, which is limit of s go to 0 and s times ys. Don't forget about this s over here. We have s times ys. Okay, which is limit of s go to 0. So we just replace this ys by what I already computed over here. So s times 2 divided by s times s squared plus 5s plus 6. So this s will be cancelled out, which is just replace s by 0 for remaining s we have. So it's 2 divided by s squared 0, 5s is 0, and plus it, which is 2 divided by 6, which is 1/3. Okay. So that's the solution for all the review question. Please send me email if you have any question about about the solution to any of these questions.